Yeah. Okay, so lecture 63 is on friction. So we'll actually do 2 lectures on this, one today, one tomorrow. Today we're going to talk about what friction is and how we can measure it, I guess you'd say. To start with, let's just think of a simple example of a block on some kind of table, right? So this block, right, will definitely have a gravitational force, m times g. And the reason it's not falling through the table and plummeting to the center of the earth is because the table is exerting a normal force on it, such that these two forces are canceling out and we get no acceleration. Okay? Now, I want to imagine imposing a force. I'm just going to call it big F. Okay? Also, this should be minus mg. We'll have this be the positive direction. I'm going to impose a force from the right in an attempt to slide the block across the table. Okay?
Okay.
But let's say that we haven't pushed it hard enough, because you all have experience with trying to push things, right? Such that it doesn't yet move, right? So there's some frictional force which always operates in the opposite direction. I'm going to write that with a lowercase kind of scripted f. Is that the best I can do? I don't know. Let's see if I can make a better f. There, something like that. Obviously this is acting in the opposite direction, so we'll call that the negative direction. Opposing the push, right?
Yeah.
Now at some point, of course, it'll move, but I don't want to focus on that just yet. I want to talk about this situation where we push just enough, right? So if we call this x, we call this the y direction. Then in the y direction, let's say that the sum of the forces in the y direction, what are they? Well, in the positive direction we have the normal force, right? And in the opposite direction we have the weight of the object, right? Minus mg. So it'll be minus mg. This is equal to 0. This, of course, means that the normal force is equal to the weight, right?
Yes.
What about in the x direction? Well, if we sum up the forces in the x direction, what are we going to get? Well, we've got the force that we're pushing, F, and then we have this resistive force, this force that's pushing back against us, minus F. See if I can make that better. Minus F. And if it's not moving, then it's equal to 0, okay? And so I'm going to say if big F is less than or equal to F. Now, the nature of this resistive force, right, so what if big F, if the force that I push on the block with is less than the frictional force, it's not like it's going to accelerate in the backwards direction, right?
Yeah.
Because this force, whatever it is, will only push as hard as I push, right?
Yes.
Does that make sense? It's kind of an important idea to get your head around. If you just looked at this blindly and you didn't know what was going on, you say, well, if F is less than little f, the frictional F, then it must be accelerating in the negative direction, because that means that the little f is bigger. And so we have a equals minus m times a, the acceleration in the x direction, right?
Yes.
But that's not the way this force works, okay? It's like it turns on, okay, and it will match whatever force you apply up to some point, and then things are going to change. And we'll talk about those changes in a minute, but first let's talk more about what this force is. It's an empirical force, okay, meaning that we don't have like calculations from first principles that will predict the magnitude of the force. You can't use quantum mechanics, for example, to say, oh, well, the frictional force for this material is going to be so-and-so, okay?
Okay.
It's purely empirical, so we get it by measuring it, okay? And in this lecture, we're going to talk about how we would measure these frictional forces. What is behind it? Well, what is behind it is electrostatic interactions, okay? So, well, let's look at the microscopic level. So if I were to like zoom in to this little spot right here where the block is touching the table, right? And look at it really close up. So kind of get a zoomed in view. We'd have the block would be a very rough, jagged surface. And this would be the block, and the table would also be kind of jagged, right? These, of course, are touching somewhat. Table. Let's say we had a block and we were testing it out on a table, and then we went and let's say it's a wooden block, okay? And I just did a test. I just pushed the block a little bit to see how easily I could slide it, right? Maybe I even had some kind of force meter to measure how much force I would have to apply before it moved, right?
Yeah.
And then I would take the block after doing one set of measurements and get some sandpaper, like some really fine grit sandpaper, and sand it really, really smoothly. So I went from something that was extremely jagged to maybe something that was a little less jagged. Maybe something like this. So the jaggedness of it is vastly diminished, right? That's a much smoother sanded surface. Do you think the friction is going to be less if I sand the block really smooth?
Let me think. Yes.
Yeah, the friction is going to be less. It's going to slide much easier, right?
Yes.
In fact, if I was designing something for the specific purpose of sliding, I would probably want to make it as smooth as I could, right? Yeah. And so the effect here, you can think of this jagged terrain, right, as kind of getting locked in place as it's trying to move along, right?
Yes.
And so you have to get it out of those little valleys and hills, right?
Yes.
So that's one way to think about it. Now at the molecular level, of course, there's not necessarily chemical bonding per se, so much as it is these weaker kind of bonds, things like, well, they have names like London forces or dispersion forces, physisorption, right? It's this kind of sticking that you get. It's electrostatic, but it has to do with stuff that's a little bit out of reach right now for us. Well, depending on how much chemistry background you had, I suppose. Okay? You can imagine if you have a chemical which has a slight dipole to it, right? Then it's going to have a little bit of an attraction electrically. Okay?
Okay.
And so things will tend to stick to it a little bit. Water is kind of a sticky substance if you think about it, right?
Yes.
Yeah, it likes to stick to stuff. But if you make the surface a little bit slicker, maybe by waxing your windshield, the water will bead up. Instead of sticking to the surface, it'll bead up and roll off, right? Because your windshield is always angled.
Yes.
Okay? So some people do that. They'll wax their windshield so that when the rain falls on it, it'll bead up into little drops. The beading is actually, it's just the surface tension. It's the water trying to minimize the surface tension. It forms these little balls, and then now it can just slide down. Okay? If you don't have that wax on, it'll tend to spread out over the glass and stick to the glass a bit more, and you have to use the wiper to wipe it away. But yeah, at its very core, though, it is electrical. It's an electrical phenomenon. It has to do with the outer shell electrons of the table interacting with the outer shell valence electrons of the block. Okay?
Okay.
But we don't need to know any of that stuff. All we need to know is that there are two types of friction. We call one static friction. That's the friction we're talking about now. The friction that keeps it from moving, right?
Yeah.
And then what we call kinetic friction, which is the friction that you get once it already is moving, right? So once I get the block to move, right, you can feel it's resisting its motion, right? It's not just going to take off and slide on forever, right?
Yes.
It's going to, if you stop pushing, it's going to come to a stop because there is a frictional force resisting its motion, okay? And that's called kinetic friction. And we'll see both of them in this lesson. I can write down really quick that the static friction, called F sub s, is equal to, usually they use mu as the coefficient of friction. So mu sub s, this is something you measure, times the normal force. Okay?
All right.
And the kinetic friction, which I'll write F sub k, is equal to mu sub k times the normal force, where mu sub s is greater than mu sub k. Wouldn't make sense the other way around, right? Yeah. So it's kind of hard to get it moving, but once you get it moving, and you probably have experience with this, trying to push something heavy. Once you get it moving, you can keep it moving a little bit easier than it was to get it moving in the first place, right?
Yeah.
Why the normal force, though, right? You think, well, shouldn't it be like proportional to the area, the amount of surface contact it has, right? If you first think about it, that kind of makes sense, right? If it's stickiness, right, that you're trying to overcome. Turns out it's not proportional to the surface area, okay?
All right.
And the kinetic friction, right? Shouldn't that be like proportional to the velocity? Well, yes, it is, but within the limits of like a centimeter per second up to maybe 10 meters per second, it behaves like a constant. After that, it tends to increase with velocity, right? And we'll talk about that kind of stuff tomorrow when we talk about air resistance. That's another kind of friction, okay? So the kinetic friction will depend on the velocity if you're not within those ranges that I mentioned, if you're not moving at a relatively slow pace. The static friction really depends on the material, right? It's rubber versus ice, right?
Yeah.
It's hard to push a block across a rubber table, right, or a rubber mat, because rubber's it's got a lot of friction. But pushing it across ice is pretty easy, right? That's why ice hockey works. You can slide that puck across the ice, and yeah.
Yes.
Now I think I've said everything I want to say about that. We'll move on to how to measure it. Suko, did you want to erase? No? Okay, so here we've got our classic inclined plane. We've done inclined planes before, right? What's different about this inclined plane is that we've added friction to it. So we have a frictional surface now. And what we're going to do in our experiment is we're going to raise the incline. The angle theta is going to start out at a low angle, like maybe 10 degrees, something like that. And then we'll start ramping it up slowly until the block just starts to slide. Okay? And when we're going to record what angle it just starts to slide at. We're going to call that the critical angle. After that, we're going to measure the acceleration of the block experimentally. And these are the two measurements. We'll use the critical angle theta sub c, we'll call it, to figure out what the static coefficient of friction is. And we'll measure the acceleration once we're above the critical angle. We'll measure the kinetic coefficient of friction using the acceleration that we record by seeing how much the block accelerates, right?
Yes.
So this is a good opportunity to practice our free body diagram work, right? This is how we use Newtonian physics to analyze systems, statics and dynamical systems, right? And so good drawings always help. And so what I would do, because I always get confused when I draw the inclined plane, so what I like to do in my mind is rotate my coordinate axes, right? So that the x direction is in the same direction as the incline, right?
Yeah.
I want to draw over here the xy axis like this, okay? Now, if I rotate my x-axis, right, to match up with the angle of the incline, right, then what is happening to this force of gravity here, right? It's no longer pointing straight down in the minus y direction. It now starts to tilt up like this in this direction, right? So here's my minus mg. My normal force, I'm not going to worry about, my normal force is going to rotate up until it points straight up in the y direction, right? Because it's perpendicular to the ramp, okay?
Okay.
So my normal force will be in this direction, just like this. We'll have a normal force coming up here. And we need to look at the components of this. We're going to have a component of the gravitational force, right, which is contributing to this normal force. I've drawn the normal force way too big as it stands. Something like that, maybe. This angle is the angle of incline theta. That's how much I have to rotate my normal, my x, y axes, right, in order to match this incline, right? It's exactly theta I rotated. And so that's going to make the angle from the x-axis to minus mg, the gravitational force, be theta. Now, the component, we want to look at the components of force. So the sum of the forces in the y direction. Well, we've got the normal force, of course, right? But we also have this component of gravity right here, which is minus mg times the sine of theta. Did I mess something up? Yes, I did. I've made an error here somewhere. Let's see. Ah, I see my error. Yes, now I've got it. Got the angles wrong here. Theta is this angle. honest mistake. So now, yes, there we go. And so the component of gravity in this direction, right here, right, using this angle theta, is minus mg times the cosine of theta. Okay?
All right.
That's the because that's the adjacent angle, right?
Yeah.
So minus mg cosine theta. And since there's no acceleration in that direction, right? It's always on the incline, right? It's not hopping up this way, right? Or falling through the floor of the ramp. The acceleration is 0. So that means that the normal force is equal to mg cosine theta. Some of the forces in the x direction, that's what we need next, right? So what do we have in the x direction? Well, we didn't write it in, but we do have the frictional force, which is in the negative x direction, and we have a component of the gravitational force, which is in the positive x direction. And this time this will be equal to mg sine theta, and this will be minus f, minus a little f, okay? So the sum of the forces in the x direction are mg sine theta minus f. And that will be equal to 0, because remember, we're interested in it not moving, right? We're assuming we're applying a force. Did I forget a force here? Oh, I'm not pushing on it. It's gravity that's pulling on it. My bad. So we're good. We're raising the angle until it just starts to move, okay? So the last measurement that we're interested in is where it didn't move, okay? I'm assuming that when I turn the knob just a little bit to raise it up a little steeper, it's going to start sliding, okay?
All right.
So, in fact, I'm even going to call this critical angle, okay? In reality, we'd have to do a number of measurements before we could say, well, this is the critical angle, because the next time we increase the angle just a little bit, it starts sliding, okay?
All right.
All right, so we have our equations. What can we do with this? Well, we can solve for F here, all right? So the frictional force is equal to mg sine theta. Why don't you guys go ahead and divide F divided by n for me on your whiteboards. So I want to see what is the ratio of F over n.
All right.
What do you get? So the relevant quantities here are this, F is this, n is this. This should be critical angle. Are you getting anything, Gabriel?
I think it's tangent. Yeah.
Tangent of theta sub c, right?
Yes.
Yeah, so F over n is the tangent of theta sub c, okay? Now, I can multiply both sides by the normal force, right? I'm going to just do that here. And I'm going to recall from earlier, we had said that the frictional force is equal to mu sub s, because we're talking about static friction right now, times the normal force, right?
Yes.
So I can replace F with mu sub s equal mu sub s times the normal force equals the normal force times the tangent of theta sub c, right?
Yes.
If I divide both sides by the normal force, this is the same normal force, right?
Yes.
They just go away. And so there I have it, right? The static coefficient of friction is equal to the tangent of the critical angle. So once I've got this critical angle, let's say it was, I don't know, 30 degrees, right? What is my coefficient of friction? Who can tell me what the tangent of 30 degrees is? What is the sine of 30 degrees?
That'll be 1 over 2.
Yeah, and what is the cosine of 30 degrees? It's the same thing as the sine of 60 degrees.
Square root of 3 over 2.
Yeah, so we have square root of 3 over 2, right? Which we're dividing by, sorry. We're dividing by that, so we'll multiply times 2 over the square root of 3. And we get 1 over the square root of 3. Can someone punch that into the calculator and tell me what it is? I think the square root of 3 is like 1.7 or so.
0.577.
Yeah, so if theta sub c is equal to 30 degrees, then the static coefficient of friction would be what? What was it?
0.577.
And I'll take your word for that. Okay?
Okay.
All right, so that is the static coefficient of friction. What about the kinetic coefficient of friction? How do we get that? Well, we'll get rid of the sub c subscripts because this is no longer the critical angle. We've exceeded the critical angle, right?
Yeah.
The sum of the forces in the y direction is still 0. Nothing's changed there. But the sum of the forces in the x direction, right, it's now accelerating down the track, right? So this is no longer true. Now this is equal to the mass times the acceleration in the x direction, right?
Yeah.
So let me just replace minus f with, call this f sub s. Now we look at f sub k, which is mu sub k times the normal force. So this is minus mu sub k times the normal force is equal to mass times acceleration in the x direction, right?
Yeah.
I want to substitute in for the normal force here with this from the y direction, right? The normal force is equal to mg cosine theta.
Yeah.
So this gives me mg sine theta minus mu k times the cosine, well actually, mg times the cosine of theta, making this substitution in for the normal force, is equal to the mass times the acceleration, right?
Yeah.
And what we want to solve for here is the mu sub k. We want to know what is this coefficient of kinetic friction, okay?
All right.
So can someone solve that for me? Tell me what mu sub k is equal to. Just a little algebra.
Okay.
Maybe Gabe could do it. Let me see your calculations. Did you?
No.
That's what I thought.
Get.
No, did you get it?
No. I think I would get it.
You know how to do algebra. So I have some trouble with the algebra. So with something like this, first thing I would do, since I see that mass appears in all three terms, I just get rid of it, okay?
Okay.
That means divide it out. So mass goes away. That's gone. Okay. I see that we have a g in these two terms. I might get rid of the g as well, but I can't completely get rid of it because there's not a g here. So this is a sub x over g. That's kind of an interesting quantity right there. That's the acceleration that you're getting versus the maximum acceleration, g, right?
Yeah.
The next thing I would do, since this has a negative sign in front of it, I'd move it over here and move this over there. So what would that give me? That would give me mu sub k, it's a terrible mu sub k, times the cosine of theta equals the sine of theta minus a sub x over g, right?
Yeah.
I would then divide out both sides by the cosine to get rid of the cosine, so that I had mu sub k all by itself, mu sub k, and then sine divided by cosine is just a tangent, so I make that into a tangent. And 1 over the cosine is called the secant, so if I didn't want to write 1 over the cosine, I'd just write times the secant of theta here. So here's the same tangent of theta that we used to get the static coefficient of friction before, right? So this term minus the ratio of the acceleration to the maximum acceleration of gravity times the secant. Okay?
Okay.
That's the term. And so once you've measured the acceleration, this was our variable that we measured, right? The angle doesn't make a difference so much, though it's not obvious that it doesn't. But really the real experimental parameter that you're measuring here is the acceleration. And so once we have that, then we have mu sub k set. I mean, so if we had a slightly different angle, we would also have a different acceleration, okay? And so we should, however, get the same mu sub k. Okay, yeah, so this is how we would determine the coefficient of kinetic friction by measuring the acceleration of the block as it slid down the ramp, okay? So I'll leave it as an assignment to you to solve for the acceleration. Let's say that we knew what mu sub k was, right? And Galileo was setting up another one of his experiments, right, with inclined planes, and needed to know what angle that if you use a certain angle, what acceleration he would be getting, right? And you could derive that from this if you knew these parameters. But you can arrive at an expression for the acceleration simply by doing some simple algebra in this case, by mass. It's almost there. So that's all I'm going to talk about in this lesson. In the next lesson, we'll talk about a different kind of friction, like air resistance. Okay, and we'll say as much as we can without using calculus and differential equations. So that's it for now.